Welcome everyone. In this video I'm going to talk about a board which I have introduced before, but now I'm going to show you another application of this board. So this board might be already familiar to you if you have been following my channel for a while. It's a very nice red PCB, and I made this to make it possible to read the DROs, for example this guy here, with a microcontroller, and then send the, let's say, output signal to a display, which is, for example here, it's an OLED display. And then this DRO is used in different kind of machines, for example a milling machine or similar equipment. So you can use this and attach it to the Z-axis, for example, and then if you have a spindle in the machine, you can read its distance or displacement, or you just attach it any kind of axis which you want to know how it moves and what's its position. So that was the past video, and that circuit is actually here. So this circuit is made on a PCB, and it's a very simple circuit. Here is a 3.3 watt voltage regulator with its necessary capacitors, and there is an LED with a resistor just to show that the circuit is powered on. And then here is an AT-Tiny85 USB port, because, for example, this guy here works with a USB port, but I also added some jumper pins. So if you want to connect cables, like I did this with this other encoder, then you can do that as well. And finally, 4 more pins here for an I2C display. It doesn't have to be this specific display, but the software I wrote is valid for this display. And then finally here you can see that there is a button with a pull-up resistor. This is just for tearing the calculation, or not the calculation but the position, but that comes from a calculation. So wherever you move the let's say carriage, you can press this button and you can reset the position to 0, and then from this new position we will calculate the new displacements. So then what's this video about? So now you can see that I have already suggested that there is a new encoder, and with a slight modification of this circuit without changing anything on the PCB, and with some modification in the software, which I will show you line by line, you can use these kind of encoders. So this is like a much better encoder. It can be used also on, as you can guess, rotating stuff, but of course you can use this rack and pinion arrangement, and then you can let's say determine linear displacement with this as well. It just all depends on the mechanism which is attached to the shaft here. And this has a bearing, and it has like a clickless rotation. So that's very nice because there is no sound, there is no mechanical resistance, so this spins freely. And I don't want to open this thing, but inside this there is a very fine let's say mesh engraved, or somehow formed on a disk, and then that is being read by a optical gate or something like that. So this mesh in this sense has 360 slits. So whenever a slit is passing in front of this optical detector, a pulse is generated on 2 different outputs. So this works exactly as a normal rotary encoder, but the principles how the pulses are made is a bit different. And then this is a very simple 360 PPR encoder. So it means that the resolution of this is 1 degree, because it generates 360 pulses by 1 full turn of this shaft. And it works with 5 volts, so that's why we need to have a small modification to this board. And that's all we have to know about this. And the rest will be shown in the coding, how it's done. So basically, I will just show you with a new build that I will rebuild this circuit from kind of scratch and show you what parts we need to modify or actually just skip to make it compatible with this kind of encoders. So I have these nice PCBs, and I have already shown you one, let's say, process of this, but this is from the same source as you could have guessed, and this PCB is provided by the sponsor of this video, PCBV. So PCBV is a service provider specialized on PCB manufacturing and PCB assembly, but they also have other services such as 3D printing or CNC machining. And I would check out these two other services as well, because now, as you can see, they have 10% off, and it's relatively simple to order from them. So you just click here on the CNC-3D printing tab, and then you click add files, and you immediately get forwarded to this website where you can add different formats of files, where you can upload your 3D design, and then you can get it machined, printed, or manufactured in another way as well. But if you are interested in their more traditional services like PCB manufacturing and PCB assembly, all you have to do is to click on PCB Instant Quote and then Quick Order PCB. And after adding your Gerber file, you can customize your board, you can add the new color, and you can add the different kind of surface finish. If you need, you can add the stencil, you can have them assemble your board and get the parts. And once you saved it in your cart and paid your order is ready to go and will be produced very fast. So I hope you will like PCBV services and products, and you will visit their website and use their services for your own project or for this specific project. So now all I want to do first is just show you that this circuit works. So I will just get some cables, and then I will connect here the 5-volt input just to power the encoder, and here another 5-volt has to be connected because of the encoder, and then everything will be shown on the display. So I will just get a few cables and show you how this thing works. So I have assembled the circuit, and you can see that the display is already running. I'm using another camera which probably will provide a better image of this display. So hopefully I will be able to show it on the video. So you can see that there are two lines. One is for the position and one is for RPM. So for a fun exercise, I just added a piece of code which checks the position of the encoder every 200 milliseconds or around 200 milliseconds. And based on that, it tries to extrapolate the RPM. But of course, all these things only work if the speed is a constant speed and there are no sudden changes and so on. But if we assume that, and if the circuit really works like that, or if the rotary encoder is being rotated like that, like with a constant speed, then the RPM value will be quite accurate. So now I should mark this encoder somehow, just to show you that this works really. So I will rearrange the things so you get a better view on the top of this knob here. So hopefully it is visible. I put a red mark here, and this will be our, let's say, reference point. And then I will just show you that this rotary encoder should work. And if I'm precise enough, I can do a full turn, and we can check always on the video because I can put an arrow here. And then we can check if this was really 360 degrees. But you can see that it works 720, and then 1080, and so on and so on. And if I try to make like roughly 1 turn per second, that should be 60 RPM. Yeah, we are somewhere there. Of course, I'm not a machine, so I cannot keep it. And as you can see, if I rotate this thing clockwise, then the value increases. But of course, it works the other way as well. And you can also see it on the RPM value, that if I go counterclockwise, which is the negative direction, then the speed will be also indicated as a negative value. And if I go roughly 60 RPM, then you can see that works. And of course, if I pass the, let's say, position, towards the negative range or domain, then also the position becomes negative. And then these values are actually the total angular displacement. So this means that I went backwards, let's say 2.5 turn from the original start position. And if I press this button here, then of course there is a jump in the RPM, and it stays like that because the display is not refreshed. But there is a jump in the RPM because we calculate the RPM based on the most recent value and the currently read value. So then that jump will produce a new RPM value. But you see that the position now becomes 0. And if I start to turn this thingy, then positive direction again is positive, negative direction is again negative. And as you can see, the display is not blinking or updating. It's not flashing, because the display is only being updated when I rotate this knob. And then whenever the calculations are finished and the knob is not moved anymore, then the display remains constant. So you can see that this thing works, and it works, I think, well. So now my task is that I should use these things which I prepared here, and I just build another version based on this PCB from PCBV, and we will just test if that circuit works. And then if it works, we just go to my computer and we check how the code works. So here is the nice board, and I cleaned up everything. So I will start with the, let's say, more simple task, which is just adding this tiny part for the chip, so a socket, because this is one of the lowest parts. So if I start adding the things which are sticking out more, for example this 4-pin jumper pin, then that will make my further work a bit more difficult. So then this just goes in. So the socket is in, and then I can add, for example, the LED and its resistor. So the LED comes here and the resistor comes here, and I just pick the regular green LED, and I also picked a smaller resistor to it, a 1 kilo ohm resistor. Hopefully that will be fine. So this part is done, and then I can go with the button and its resistor. And then I can start to add the jumper pins. So I add the 2 jumper pins, one for the display and another for the DRO pins. And then I will add 2 more, one for the plus 5 volt input, because I made an alternative choice between a USB port and a jumper pin, because these are SMD USB ports and they might be difficult to solder. So then I add those. And then another pin is added here at the top, which actually shorts out the input pin of this voltage regulator and the output pin. So then we just directly direct the plus 5 volt towards the rest of the circuit. And now I can use this tiny jumper cap and just use it to short it together. So now this is done. So we skipped the voltage regulator, and then now I have another task. Is I can try to add these USB ports and see if I can solder them properly. So I will add a little bit of solder paste, and then I will use my heat gun to try to solder these tiny pins of the USB port. So after some struggling, the board is ready. So now all I have to do is I just place the 80 tiny from that board into this board and wire it up and see if it works. So let's do that. So I have prepared everything. Here's the display, here's the rotary encoder, and here's the new circuit. This is the old one. And I will be brave and I will trust my soldering. So I will directly connect this to a USB connector and see if the things are working as they should. And it does. So you can see it on the display. You can see the position. You can see that it works via USB. You can maybe even see a slight green LED there. So now I rotate this one full circle or a bit more, and we are at 376. I can tare it, I can go backwards, 360. So as you can see, it works. So now the new circuit is capable of handling this kind of rotary encoder in addition to this kind of DRO. So that's really nice because we can use the same circuit with multiple devices. We just need to change the code on the 80 tiny, but that is actually relatively simple. So let's see how that is happening in the microcontroller. So let's go to my computer and I will guide you through my source code line by line. So this is the Arduino code and I'm using it on an 80 tiny 85, but with a slight modification you can use it on any kind of Arduino based microcontroller. So the principles will be the same and most of the code will be the same. So I'm using this 80 tiny, so I have to use a different kind of libraries. So I'm using this tiny I2C master.h for the I2C connection, and I use this tiny 4K OLED for the SSD 1306 OLED display. And then I have this character array here, and this will hold the string which will be printed on the display as a value, for example the RPM or the position of the encoder. And then I have this typical timer that I usually use. This will be just counting, and it will not let the microcontroller to enter the function which handles the button for a certain period of time. And then these are the pins for the rotary encoder and for the tare button. And you have to be careful, or just keep in mind that these pins are not the physical pins as you would count them on a regular 8-pin chip, but you should always look at the drawing of the 80 tiny and see which is the pin 1, 3 and 4. And you can see it how I did it. And then you know that the rotary encoder is always generating sort of a change. So it generates two square waves on output A and output B. They are shifted a little bit by like half wavelengths or something like that. And then based on the relationship between these two shifted signal will tell us what was the direction, for example, and if a click or a movement happened on the rotary encoder. So we will have to store the states which we just read when the rotary encoder was moved, and the previous states, because they will help us to determine the direction. So that's why I have these four things here. And then comes the variable, which is like the rotary encoder's position. And then we have the result position, which is like the tared value. So if we have a tearing done somewhere, then we save the value of the rotary encoder at that position, and we subtract it from the current position. So at that moment it will be 0, and whenever we move the rotary encoder, depending on where we move it, it will be a negative number or it will be a positive number, like 1, 2, 3, 4, and so on. And this is the recent result position. So that is the most recent reading before a new position is being read. And this is important because I use this variable to keep track of the change. So if I see that there is a difference between this number and this number, I can tell the microcontroller that there was a movement on the rotary encoder, so it should, for example, update the display. And the tare value is just the value of the result position when the button was pressed. So if you press the button, you will see it in the code very soon, that we pass the value of the result position into or to this tare value position. And then value changed boolean, so this keeps track of the value change, so I can tell at different parts of the code to the microcontroller that it's time to update the display, for example. So I will use this mostly for that. And as I said and showed, there is an RPM value also shown on the display. So I just kept a few variables for this. So this is very self-explanatory that we have the RPM value. And then the RPM interval is like how long time we should, let's say, measure the rotation, and how long should it take to determine the RPM. So now this is a very quick measurement. So I just measure for 0.2 seconds or 200 milliseconds, and then I calculate the RPM. So this is how this works. If you change this, of course, let's call it integration time, that will be longer. But then the update frequency of the RPM value will be, of course, more sluggish. And then the timer is also keeping track of the elapsed time. So that just helps us to keep track of it. You will see it how. And then this is like the time difference, because I just say in the if condition that if the elapsed time is larger than the interval that we gave here, then we enter the function. But I don't determine how large it should be exactly. So then this variable will hold the exact value. So I will not use, let's say, 200 milliseconds in my calculations, but maybe 235 milliseconds, just to be more exact with the numbers. So then we have the setup function here. This is also very simple again. We have 3 inputs which we have to take care of. The 2 pins from the rotary encoder and the 1 button on the circuit board, which is the tare button. So all of them have input pull-up inputs. And then at this moment, I just read the current status of the CRK and DT pins, and I just save them. And then actually the ATtiny85 doesn't really behave well when you want to determine the interrupt pin in a regular way with this attach interrupt, and then in the argument you have 3 different things that you can determine, like what should be the pin, what should be the function that should run when an interrupt happens, and what should be the condition, like falling, rising, or change. So instead of that, we enable the interrupts with this, let's say, hard coding or bit banging, and we enable it on the PB4 pin, and we just turn on the interrupts with this. So this is basically equivalent with the attach interrupt function, but that doesn't work on the ATtiny. And then this part is just the display. It's quite simple. So here we just have to define which kind of display we use. I clear the crap because when we start up there could be some kind of any kind of things on the display. And then I print the permanent part. So you know that there is a position and an RPM written as a text on the display. So this part handles that. So I pick a small font. I move to the x0, y0 position, and then I print the text position. And then I move to the x0, y4, and 4, if I remember correctly, that is the line number and not the y coordinate. So 4th or 5th line, and then I print the RPM as a text, and then I turn on the OLED. So I guess this passes the value to the buffer or something like that. And then I change to the new font, because after this line, whatever will be printed on the display, first of all, will not disturb these lines, but it will be printed with a larger font. So then in the loop, I have just 3 functions, very simple functions. Read button, so we are just polling the tare button, it's perfectly enough. And then we have the print LCD, so this will run when we have to update the values on the LCD. And calculate RPM, this is also self-explanatory, so it calculates the RPM value. So what happens in the read button, based on my connection and circuit design, I'm looking for this condition. So when I press the button, the input pin is being pulled to the ground, so its value becomes 0. And when its value becomes 0, then we can perform these parts of the code. And what happens here is that we first check if at least 300 milliseconds elapsed since the last time when this condition was true. Otherwise, we treat that thing as a bounce, so we don't enter this function. So let's say there was more than 300 milliseconds elapsed. So then what we do, as I explained earlier 5 minutes ago, the tare value is the rotary position. So we use the most recent reading from the rotary position as the tare value. So at this moment, when you will look at the display and we press the button, then the position will be updated to 0. And then I just pass the current time to the button timer. So then from this line of the code, we will have to wait 300 milliseconds again to be able to press the button and initiate some kind of change again. And I changed the variable to value changed, because we have to let the microcontroller know that it's now allowed to update the display. So since we want to update the display, it's very handy that we have the print LCD function after this. So as I said, here we changed the variable to true, and then this function checks that. Is it true? Yes. If it's yes, then we enter this part. So what happens here is that I just do the final calculation here instead of doing it in the interrupt function. So what I do here is I just subtract the value of this tare value variable from the rotary position. But if this is 0, of course, nothing changes. And then that is the result position. And that will be printed. And how that happens is that first we have to use this function d2strf, because Arduinos don't like this kind of float to string conversion. So then we use this function which does basically the same, but instead of converting it into a string, like a traditional string, we create an array of characters, and that array of characters will be then printed on the display. So here, this is the variable that we want to print, and then this will be the precision, and this will be the string. So let's say the target array where we store the number as a character. And then I set the cursor to x30, so this will put the cursor after the text which we already printed on the display, but we start in the same line. And then first of all I clear the previous things, and then I move back to the same beginning where I was previously before erasing the previous values, and I just simply print the result position, so this, which is of course converted into string. And then I do the same, but I do it with the RPM value, And of course, I move down with the lines to the line number 4. So I think this is quite understandable. And after this printing operation is done, I change the value of the value changed variable to false. So now in the next iteration, we will not be able to enter this part. And the microcontroller will not enter this part as long as there is no change. So then here is our interrupt function. So this is how we have to define it. But then the inside of this function looks exactly the same as I've been showing the handling of the rotary encoders for years. So now when the interrupt function is fired, we read the CRK pin's status, whether it is 0 or 1. So then we check these conditions, and only if these conditions are fulfilled, we enter this part of the code. And then what happens here is that we also read the DT pin, and based on the relationship between the CRK and the value of the DT pins, we will do something with the rotary position. So if it was not equal, so they were different, then we increase the value of the rotary position by 1, because there was just one increment, of course. Or if it's true, I mean, if they are equal, because here there was a negating signal or symbol, then we decrease the value by 1. And then we save the CRK now value into this CRK previous, and we again let the microcontroller change the display in the next iteration. And finally, we have the RPM calculation. That's very simple, and I also put an example here, so take your time to read it. So first of all, we calculate the difference, the exact difference from the timer. So we have the millis currently, and we have the previous value of this millis. So this will make sure that we know the exact difference between, let's say, two parts. So then what happens here is that if the difference between entering the function here and coming back to this part again was larger than 300 milliseconds, that was here, or sorry, 200 milliseconds, and there was a change in the positions, we let the code enter. So then we can enter this part of the function. And then what happens here is that we calculate the fraction of the timer diff as compared to a minute. So we divide 1 minute, 60,000 milliseconds, by the difference here, which can be something around 200 milliseconds. It can be a bit larger, but never smaller because of this condition. So this will give us the proportion of the elapsed time. And then here we take the result position minus the recent result position. So the last time, this highlighted part here, the last time when we entered this part, there was some position, and now this example here shows from the very beginning, so it was 0 previously. And then the result position is the most recent, like in this very moment, and that is now 3600. And then in this sense it's degrees if I use my 360 ppr rotary encoder. So that means that in 2 seconds we did 10 turns, because 10 times 360. So then I also wrote it down here that in 2 seconds we did 10 turns, because 3600 divided by 360. And then if we assume that the speed is constant, then we just do this calculation. So 30 times 10, so that is 300, and 300 RPM is the final result. And that makes sense. If you make 10 turns in 2 seconds, then 1 second is 5 turns. So 5 times 60 is 300, so it adds up. And basically that's all regarding the formula, so this is not a very difficult formula. After we finished the calculation, we save the most recent, let's say, previous position. That was our position now. We kind of reset or update the timer, and we also let the code know that it can update the display, because now we have a new RPM value, so it has to update the display. So yeah, and then of course when this is true, then we will be able to enter this code, update the display, and that's all. So this was the whole video, and as you can see, it was not too difficult. The hardware changes were manageable, and also the software changes were quite simple, and you could see that it works very nicely, so we can capture the position and we can capture the RPM also very, very nicely. So if you want to get this code and download it as it is, then please consider becoming my Patreon, because if you go to my Patreon and decide to support me, you can download this code directly. Otherwise you have to copy it from the video line by line. And also don't forget to visit my website. A link is in the description. I put a link for the PCB there, so if you decide to buy it through PCBV.com, then you can also support me, but also use PCBV's services. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.